This is for ECE 3300 lab for the summer of 2021. This is lab 3, the 16-bit adder. So to start this lab, we first had to make a high overview model of the system that we are designing. A 16-bit adder on a board that has 32 switches is obviously an optimal solution, but given the constraint of the FPGA that we have to use, we only have 16 throw switches, and then we have some peripheral push buttons also on our development board. So because of this, we had to make a few different modules along with the full adder. So to start, over here we have our demultiplexer. So this A-B input is for the A and B, that's what it's referencing for the full adder. So it's 16 bits, which is our 16 switches on the board. Those enter the demultiplexer, and here is our select line right here that goes into the demultiplexer. And this will choose which path it takes, this line up here being 0, this line down here being 1. I also tied these lines to registers because we need registers to hold the values while we're inputting the value for the other input to the full adder. So up here we have our first register, register A, and we have our D input because this is just a big D flip-flop. Our enable, which is when select is low for the demultiplexer. Then we have a reset, and then we have our clock. Register B is very similar, except it's enabled when select is high. And then over here we have our full adder with a carry in and our sum, and I forgot a line, but there's a carry out as well. Okay, and now I'm going to explain the code real quick. So we have our first module, which is the demultiplexer that we were talking about. So it's given an input of size, and then our select, and then our outputs, out1, out2 is what I called them. And then I made some conditional statements down here to assign the outputs. So when select is low, we're going to pass it to A, otherwise A is going to receive a 0. And then for the second output, if select is high, we're going to pass the input from the AB switch, otherwise B is going to be low. Next we have our register. So what I did was I created an n-bit register. So to start, I made a base model called a 1-bit register, which is just essentially a 1-bit D flip-flop. So we have our input data, input enable, input reset, input clock, and our register output. So to start, I made the output 0, so that way we don't have any ambiguity when we start our system. And then I used an always block with the positive edge of the clock or reset. So if the reset's high, then the output of the D flip-flop is going to be 0. Otherwise, if enable is high, then the output will be whatever's on the data line. Then to input this 1-bit register, I made an n-bit register file, and this takes in a parameter of size, and it's essentially the same lines that we had with our 1-bit register, except our data is of size -1 to 0 and size -1 to 0 for our output as well. And then all I did in this file was I did a generate statement or generate block and did a for loop to instantiate size -1 registers. And then next we have our full adder. So I did the same thing as with a 1-bit register. So I made a 1-bit full adder, which is just I use the gate level implementation in my code. So we have an input of A, input of B, input of the carry in, and outputs of sum and then carry out. Then I made another file called n-bit adder, and this one I have a parameter of size again, and the inputs A and B are going to be from 0 to size -1, and same goes for our output sum. Then I had to create a temporary output holder for the carryouts of size to 0 So essentially the first C out temporary is the carry in, and then the last one is our final carry out, which I put after our end generate statement. Next I made a for loop and a generate block again. So I essentially instantiated size -1 full adders. So I inputted A and B normally, same with sum, and then for the carry in and carry out, the carry in was whatever was in this array of the ith value, and then the carry out is the next one. And finally I made a top file which instantiates all of the n-bit blocks that I created, with also a parameter. So I have a parameter of which I called size top for the AB switch, -1 to 0, so 16, and then same for the sum LED. I also had inputs of carry in, select, and then the resets, and then a carry out. I named them LED and switch so it's easier for me to reference inputs and outputs. Then I created some wires to hold the values between the different blocks. So the mux out 1, out 2 top, pretty self-explanatory. And same with A register out and B register out. So then I instantiated all 4 blocks, our demultiplexer with AB switch, select switch, and then the temporary output holder wires, and then n-bit registers. A obviously getting the output, which it's supposed to get out A from the demultiplexer. Enable, which here says it's enabled when select is low. A reset switch, the clock, and then the register output. And then same goes for B, except it's when select is high and it's out 2, and reset B switch. And then finally we have our adder. So we have the A register, B register, the carry in, and then the sum LED, and then the carry out. And then for our constraints file, we created a clock which is 100 megahertz, and then we have all our input switches. The AB switches are all our throw switches, and then we have all the green LEDs representing our sum, and then the carry out LED is represented by the blue LED from the 16th LED on our development board. And then finally we have 4 push switches. So the top one of the push switch in the cross orientation is select, left is B, right is reset A, and then the bottom one is the carry in. Okay, so we're going to go over the simulation now. So we have a clock of 100 megahertz, and I started with everything at 0 except the clock is high to start. So we have all values of 0 right now except the clock. Clock goes low, everything's still 0. Then the clock goes high, and our input for A is 65,535, which is just FFFF in hex. And then the clock goes low, and then I toggle the select, so now both are at FFFF in hex. We can see that our carryout works and that we get a sum of 65,534. And then at the next clock cycle, I set a carry in, so then we have our carry out plus the max value at the sum. And then I put the select low again, but then I change the input value to be 255. And that means that our B register is still holding the max value, which is why we still see a carry out, and 255. Well, we also get 255 because there's a carry in still. At the next clock cycle, I set the select high, and then I have the next value at 245, hence we get the value of 501 and our carry out goes low. Then next the carry in goes low, so meaning we get a sum of 500. And then at the next clock cycle, I set the reset for both registers high, which is why we get an output of 0. Then at the next clock cycle, I set the input to 25 and the select low, so now our A register contains 25, which is why we get a sum of 25. And then at the next clock cycle, select goes high again, and that's why we get a sum of 50 with no carry out. Okay, and now to wrap it up before we get to actual board demo, we can see that our utilization right here, we have 18 lookup tables, 38 bonded IOBs, and then our power summary, we have 118 milliwatts of power. Okay, so I just uploaded the bit stream to the board. So as of right now, both registers are cleared. So this is our select push button. This is the carry in, as you can see here. This resets register A, and then this resets register B. Okay, so to start, since our select is low, we're going to be loading up register A, and we're just going to flick on all of our inputs right here, since I will be copying our test bench right here. So right now we have 635 at A, and we can see that our sum matches. And then next we're going to do our, we're going to load register B with the same value as well. Okay, and then now we can see that our carry out is high, and that we have a sum of 65,534. Okay, and then if we add our carry in, we can see that all the LEDs are on, which is right. Okay, so now I'm going to clear both registers, and well, because the switches are high, actually we can see now that I just have these two on, that our reset works for A. Okay, and then now I'll add some basic values like 2 plus 2. We can see that that is 4. And this concludes Lab 3 for 3300.